To be honest, the terminology of the numbers, which number is a natural number or a prime number or a whole number or a real number, it was never my favorite topic. I mean, why do I care? I understand numbers. Why do I have to know if it's a whole number or a real number or a natural number or a rational number or whatever it might be? But then I learned that there are very interesting historical stories related to the development of these numbers. And those stories made it so much easier for me to remember which number is a natural number, which one is a whole number, which one is an integer, and so on. So hopefully, when you hear those stories in this lecture, it's going to help you understand and remember the number system. Our story takes us back to those times when humans had not mastered any language yet. They had no words for a lot of things, let alone the number of sheep that would leave the pen in the morning and come back in the evening. How would the shepherd know that all of his sheep that left the pen in the morning is coming back to the pen in the evening? But we know humans are smart. If there's a problem, they would come up with a solution. And the solution was, every time that a sheep walks out of the pen, the shepherd would put a rock in a bag. And in the evening, when the sheep would come back, he would take the rock out of the bag. And at the end, if he has no rocks, no pebbles left in his bag, he knows that all of his sheep has arrived back home. The shepherd did not even know the total number of sheep. All he needed to know was that each sheep corresponds to a pebble. As the time progressed, humans obviously became more advanced and learned how to carve tally marks. So we have one sheep, one stone or one tally mark, two sheep, two stones or two tally marks, and so on. In today's DNA age, it may not be easy for us to appreciate it, that what a big breakthrough this must have been, the one-to-one correspondence. This is a perfect inventory management system without ever writing or naming a number. So now humans had two ways of counting. One is with objects, such as pebbles, and the second is by carving tally marks into wood or stones. And if you think about it, the marks are a very efficient system of keeping inventory. Instead of carrying 5 sheep with you or 5 stones with you, all you have to carry is 5 tally marks carved on a piece of rock or a wood. A mark is not a sheep. It represents a sheep. And if you think about it, this is the first step required for algebra. In algebra, we use variables. A variable is not an object itself. It represents an object. It represents how many number of those objects, whatever we're talking about, are there. So now humans have some kind of numbers. And these numbers, they're not actually objects, but they represent objects. So now humans have developed some sort of numbers. And it was indeed a great intellectual achievement of the history. These numbers were developed to keep track of the inventory. How many cows I have, how many dogs are there, how many children I have, or maybe how many husbands I have, or how many wives I have, or whatever was important to people back then. So people could now talk about 1 apple, 2 apples, 3 apples. And these numbers, they are called as natural numbers, the very first number family, also called as the counting numbers. These numbers are used to count what's out there. So these are natural counting numbers for objects of nature. So for instance, over here, in the first pen, we have 2 sheep. In the second pen, we have 1 sheep. In the third pen, there is no sheep. So now they can communicate with others. They can tell that there is 1 sheep, 2 sheep. But what would they say when there is no sheep? How would they mathematically describe it? How do you mathematically describe nothing? And for that, 0 took birth. 0 performed 2 roles. First is a quantity for nothing, a number for nothing. Second, it acts as a placeholder, as in 204. There are 2 hundreds, 0 tens, and 4 ones. Their 0 is a placeholder. So including 0 in the number system kind of completed it, kind of made it whole. That's why it's called whole numbers. So the numbers 0, 1, 2, 3, all the way up to however far you want to go, they're called as whole numbers. So far we have discussed 2 kinds of numbers, natural numbers and whole numbers. Natural numbers, they count things that are actually there. So they begin with 1 and keep going up from there. Whole numbers include 0 and the natural numbers. So you say that the natural numbers, they are a subset of whole numbers. So all natural numbers, they are whole numbers. So now the question is, are whole numbers sufficient to describe all the things that could happen? No. Let's say I have 3 sheep. I owe you 1 sheep. So after I give 1 sheep to you, I'll still have 2 left. Let's say now out of these 2 sheep that I have left, I owe 2 sheep to another friend. So I give my 2 sheep to that friend. I have 0 left. Very good. But I owe 1 more sheep to another neighbor. How do I describe that? How do I take something out of 0? I have nothing. How do I take something out of there? So that means I owe this debt to that neighbor. How do I describe this debt in terms of numbers? Well, back then I couldn't. So the need was to describe debt mathematically, and that gave birth to invention of negative numbers. So now I have this number line where if I begin at 0, I go to the right, I have 1, 2, 3, 4, 5, and so on, keeps on going. And on the left side, I have the negative numbers. Everybody knows the meaning of this. If out of 3 sheep I had, I take out 4, I owed somebody 4, I have minus 1 left. So out of 3, if I take out 4, I will have minus 1 left here. We all know this. So now I have the 0, all the natural numbers, and the negative counterparts of the natural numbers. They are included in integers. So integers, they can be negative or positive and 0. But only if life was so easy at all the times. Now our shepherd has 1 bread loaf, but he has 2 kids. So he wants to divide this 1 bread loaf between 2 kids. How do we describe it? Each person gets 1/2. Now these numbers, 1/2, these are not integers. So this led to the invention of rational numbers. The word rational contains the word ratio in it. So rational numbers, they can be represented as a ratio, let's say P over Q, where Q has to be a non-zero number. Why? Because dividing by 0 is undefined. So any integer, such as minus 5, is that a rational number? Sure is, because I could divide it by 1 and that changes nothing. It's still going to remain equal to minus 5. So all of the integers, they are rational numbers. All of the numbers that can be written as a ratio, P over Q, where Q is a non-zero number, is also a rational number. You would think that we have already seen all kinds of numbers, but no. And now is the entry of the irrational numbers in our story. To understand irrational numbers, let's look at an example. In this example, we have an isosceles right-angled triangle. 2 equal sides of this right-angled triangle are of 1 unit each. And using Pythagorean theorem, we get the hypotenuse to be equal to square root of 2. And if you write out the square root of 2, it is 1.4142135, so on, keeps on going forever without ever terminating and ever repeating a pattern. So such numbers that never terminate nor repeat a pattern, called as irrational numbers. And as a matter of fact, all square roots, unless they are square roots of a perfect square. They are all irrational numbers. So what I mean is this: square root of 4. This is either plus or minus 2. This is not irrational. But square root of 3, since 3 is not a perfect square of any number, this is going to be an irrational number. Square root of 5, an irrational number. But square root of 9, that is not going to be an irrational number. This will be a rational number, because 9 is a perfect square of 3. Square root of 11, that is an irrational number. But square root of 16, which is equal to plus or minus 4, this is a rational number. So rational, rational, rational. So once again, square root of perfect squares, they are rational, and all the other square roots, they are irrational numbers. And similarly, all the cube roots, unless they are cube roots of a perfect cube, they are all going to be irrational numbers. Cube root of 2, it is an irrational number. But cube root of 8, this will be a rational number. Why? Because the cube root of 8 is equal to 2. In other words, 2 cubed is equal to 8. So the cube root of 8 is equal to 2. And therefore, cube root of 8 is a rational number, but cube root of 2 is an irrational number. Make sense? So just a quick review. An irrational number cannot be expressed like this. So this will not be an irrational number. If it can be expressed as P over Q, then it is a rational number, provided Q is not equal to 0. If you can put a number like this, it is rational. An irrational number, in contrast, it cannot be expressed as a ratio of two numbers. What else? An irrational number is a non-terminating number. It keeps on going forever without ever repeating a pattern. And there are several familiar examples of irrational numbers, such as pi and e. And all the square roots of numbers that are not perfect squares, all the cube roots of numbers that are not perfect cubes, all the fourth roots of numbers that are not any number to the power 4. I hope that you see the logic and the story of the number system developing over here. Moving on. Now we are about to define real numbers. Real numbers. It's an umbrella term for all the numbers that we have defined so far. All irrational numbers are real numbers. All rational numbers are real numbers. All integers are rational numbers. All whole numbers are integers. All natural numbers are whole numbers. Do you see that? These numbers, they're nested in each other. This is important, and I want to emphasize on this, that there is this big umbrella of real numbers. In this umbrella, we have two kinds of numbers: rational numbers and irrational numbers. Rational numbers can be put like P over Q. It can be put in this ratio, and here Q is not equal to 0. While irrational numbers, they cannot be expressed as P over Q. Irrational numbers, they are non-terminating, they continue forever, and no repetition of any pattern. Now all the integers, they are rational numbers. All of the integers. Then all the whole numbers, they are integers. Whole numbers are 0, 1, 2, 3, and so on. And then all the natural numbers, they are whole numbers. What are natural numbers? They are the counting numbers like 1, 2, 3, 4. So natural numbers 1, 2, 3 going up, whole numbers 0, 1, 2, 3 going up, integers. All of the natural numbers and their negative counterparts and 0. Okay. Rational numbers, they can be expressed as P over Q. P is an integer, Q is an integer, and Q cannot be equal to 0 here. Irrational numbers, these are the numbers that cannot be expressed as P over Q. And these irrational numbers, they never terminate and they never repeat a pattern. And the examples of irrational numbers are all of the square roots that are not perfect squares, and likewise all of the cube roots that are not perfect cubes. And taking it further, if you talk about fifth root, let's say fifth root of 32, would this be rational? Yes, this is rational. Why is it rational? Because is equal to 2, and 2 to the 5 is 32. So since 32, it is fifth power of 2. That means fifth root of 32 is a rational number. But the fourth root of 32, that would be irrational. Now it is irrational. Make sense? In other words, if I were to generalize it, I would say this. If you have nth root of a number that is x to the power n, so any number that is x to the power n, and you take its nth root, then that would be rational. But if you have nth root of x to the power m, where m is not equal to n, then it is irrational. I know it's kind of abstract. Maybe you're not used to seeing so many variables and symbols, but now is the time to get used to it. Why? Because we are heading into algebra, and there you're going to be seeing a lot of variables and a lot of symbols. But don't you worry, I'm here to lead your way through it. And if you have any questions, any concerns, put them in the comments. And I promise to address those questions related to what we're doing. Alright, moving on. We have already discussed it, but a review doesn't hurt. So here we go. Natural numbers. They are a subset of whole numbers. Whole numbers are a subset of integers. Integers are a subset of rational numbers. Rational numbers are a subset of real numbers. Now, what are non-real numbers? Well, when you learn about complex numbers, imaginary numbers, you're going to learn about non-real numbers. So here on this slide, I have listed all the number systems that we have discussed so far. One more time. Natural numbers, they are the counting numbers, 1, 2, 3, and so on. These are natural numbers. Whole numbers, they include all of the natural numbers and 0. So whole numbers are 0, 1, 2, 3, and so on. Keeps on going forever. Integers. Integers are all of these numbers and their negative counterparts. While 0's positive, negative is still 0. So it will be like -2, -1, keep on going on either side. 0, 1, 2, 3, and so on. Next is rational numbers. What are rational numbers? On this side over here, they can be expressed as a ratio of, let me not use uppercase Q here, let me use a lowercase q. Rational numbers can be expressed as P over Q, where Q is not equal to 0. Irrational numbers, non-terminating and non-repeating patterns. And all of these numbers, all the numbers that are listed above the real numbers, are part of real numbers. Real numbers include all of these numbers. Hopefully, this lecture made sense. I tried to tell a story with this lecture, how the number systems, they developed as per the need of people of that time. When I understand something with the story, with the logic, it sticks in my head. And until I learned about this history of the number system, I'm telling you, I really had a hard time remembering which number system was which. But now that I know the logic, I know the reason, It just makes sense and I don't forget it. Hopefully it will work for you as well. And now is the time to move to our post-test. This post-test is going to be very straightforward and very short, just like the pre-test. Here you go. I'm going to leave it here for a few seconds for you to take a screenshot and pause the video so you can write down the answers of these questions on your paper. And this time I'm not going to make a separate video for the post-test because there's not much to discuss. There's really nothing to explain here. Either you know the answer or you don't know the answer. Done? Let's go over the answers. Natural numbers. Which of these numbers looks like a natural number? I want to say A goes with 5. Whole numbers. Well, 0 is certainly a whole number. Here we go. Integers, -8. Looks like an integer to me. Rational numbers. Aha, right across. 5/8. Irrational numbers. Irrational numbers. Square root of 7 is an irrational number. Real numbers. Negative square root of 11, well, is an irrational number as well as a real number. Minus square root of 11 is irrational and real. So is square root of 7. It is irrational and real. Alright, hopefully this lecture was useful to you. Hopefully it was not too boring or dry as this topic might sometimes be. What's going to be the next topic? I have not yet decided what's going to be the next topic, but whatever it is, you're going to see it very soon. And I'll see you there in the next pre-test.